Yes. Yeah.
Is it working?
Looks
Yeah.
good.
Yeah.
We
I
can
hope this is going to be good, Kasun. I'm looking forward to it.
Oh yeah. In my internal examiner.
All right. And then we can get started then. So yeah, welcome everyone back to this week's TBR GT Time Talk. So today we have um, a speaker from the Structures Group. So we have a cousin who recently completed his PhD, and some of his internal examiners and also PhD advisors are on in this call. So he has some experience working with some of the members in our group, but not fully. So I'll leave it up to him to fully introduce himself and his background. And today he'll be talking about his work that he did on which and a particular part of his project which was on taking measurements on to analyze the ambient vibration based bridge scale monitoring system. Um, and just some housekeeping rules. So I just want to ask everyone to please mute themselves if they're not speaking, and there'll be about 5 or 10 minutes at the end of the presentation for anyone to raise their hand and ask a question from Kasun. All right, I think it's over to you, Kasun, to begin your presentation.
Yeah, thank you very much. I mean, first of all, I have to say thank Thisal for this huge opportunity, because I mean, I know like uh, some of you are like the leading experts in vibration and dynamics around the world. So it is a huge opportunity to present my research to you, and I'm really looking forward to hearing your thoughts at the end, because some of the findings of my research are like there is still some of the more things to be explained. And so this research was on an ambient vibration based bridge scour monitoring technique. So my PhD supervisor is Professor Campbell Middleton, and my PhD advisor is actually Dr. James Talbot. And actually my research team had Professor Gopal Madhabushi, Dr. Stuart Hay, and Paul Fiedler. So scour is a massive problem for bridge engineers. So this is Malahide Viaduct, and this bridge failed because of scour. So this bridge failed exactly 10 years ago in Ireland. And after this bridge failure, and actually, if you look at some of the bridge failures that happen around the world, like more than 50% of the bridges fail because of scour. So that's a massive problem for bridge engineers. So if you look at what is scour? Scour is simply the removal of soil around bridge foundation because of the fast flowing nature of water. So if you look at it without soil, without water, we can see what's happening there. That's what's happening is because of the water hitting the bridge piers, and also because of the fast flowing nature of water, there's going to be scour holes created around the bridge foundation. So because the bridge foundation is actually supported on the soil, and if that soil support is lost because of scour, we see that the bridge is going to be unstable. So this is exactly why large number of bridges actually fail. But so to avoid this from happening, what we need to do is to be able to monitor scour. But I mean, typically we can do visual inspections if there is a crack on the superstructure of the bridge. But this is a phenomenon which happens underwater, so it's oftentimes it's very difficult to observe because there is a water layer there. So the current techniques for monitoring scour, I mean, the most common technique is actually using diving inspection. Diving inspection does not provide reliable information because diving is we can't carry out diving during flooding, and that's when the scour is the highest. And also it provides very limited amount of information. It does not provide a good accurate results. Other techniques are like ground penetrating radar. We can use a ground penetrating radar device. We can guide it at different locations and measure the riverbed using this radar. And there are other techniques such as magnetic sliding collar, which uses a collar which rests on the ground, and this collar rests on the ground, and as the ground level goes down, the collar also goes down, and using magnetic based sensors, we can actually find out where the location of the collar is. But with that technique, let's say let's say there is a certain amount of scar happening, and let's assume that there is some refilling happening, and we this color will not go up. So because of that, we can't measure that. And the most common, another second most common technique is actually using sonar. And there are sonar based underwater vehicles and sonar based, like fixed sonar based techniques. And these actually showed some good results, but there's still some problems with related to environmental sensitivities and all that. And so like this, there are a wide number of monitoring techniques that are available, but they have a number of limitations. So this is where actually these vibration-based techniques can actually uh, show some potential. So with vibration-based, I'm sure, I mean, vibration-based monitoring techniques are very common to you. With vibration-based monitoring techniques, what we simply do is we place accelerometers on a bridge and we measure the vibration-based properties. So the idea is that whenever damage occurs, the vibration-based properties would change. And the most common parameter is natural frequency, and there are other dynamic parameters as well. So the idea is that whenever there is scour, because the ground level change, these parameters will also change. To look at this from the most simple form, we can assume the whole bridge as a lump mass system. If we assume, because typically the most of the mass of the bridge comes from the superstructure. So if we assume the whole mass is lumped at the top, uh, and if we assume that mass as m, and if we assume the bridge pier to be light, and it has a flexural rigidity of ei, we have the natural frequency given by this equation. So for the case of scour, for the case of scour, so scour is basically increase of the exposed height. So the case of scour, what we have is this h is increasing, all the other parameters are constant. So if h is increasing and all the other parameters are constant, we can see that there's a significant relationship between frequency, natural frequency, and the exposed height. So we can see that, like, for this very simple case, where we actually assume that the ground level is fixed, which is not the case in real life, we can see that the natural frequency and the exposed height has a significant relationship. So because of that, you can assume that with scour, there is a significant relationship with uh, natural frequency. So there are previous researchers who actually proposed that natural frequency can be used as an indicator of scour, but there is very limited amount of information on other dynamic parameters. So in my research, I proposed we can use two other indicators as well. So vibration-based monitoring techniques are not new, but vibration-based monitoring techniques have been used for decades. But if you look at this research, the main focus has been on crack damage detection and superstructure damage detection. So with cracks, what we have is, if there's a crack, that's a localized reduction in stiffness. So with a localized reduction in stiffness, uh, the lower order modes of vibration, for example, the first mode of vibration, uh, which have a global mode shape, they don't change much because of a reduction in like local stiffness. But with scour, what we actually have is a global stiffness change, because it's actually boundary condition change. So we can expect from that end as well. Uh, with with scour, there can be a more significant effect than because of cracks. So if you look at existing literature on which were carried out on field studies to capture scour using vibration. So there is one research conducted in the US. So they have deployed accelerometers on two bridges in Texas, and on the so this is one of the bridges. But the issue is that during the time of monitoring, they were not able to capture any significant change in natural frequency. And in Japan, these researchers have been able to actually capture natural frequency at this bridge. Uh, and they were able to showcase that uh, so this bridge had about 6 bridge piers, and these bridge piers had different amounts of scour. So they were actually able to look at the natural frequency of each bridge pier and show that natural frequency of different bridge piers have some correlation to the level of scour they have. So so this research was actually successful indicating that natural frequency and scour depth has a relationship. But with this research, because they were trying to measure the natural scouring, they were not able to get enough scour that would change the natural frequency by a significant amount. So we actually decided to take a different approach. Rather than looking at natural scouring, which which is very unpredictable, we went to a bridge which has scour already. That's a Belden bridge. So my supervisor sent an email to all the bridge owners, like lots of bridge owners in the US, in the UK, sorry, and they found this bridge. This is Belden Bridge, and this bridge has three spans, and it has a history of severe flooding. You can see that the level of flooding is almost up to the level. So what we did was we went to this bridge, and because this bridge has scour already, we wanted to find out what is the level of scour at this bridge. So what we did was there's a sonar scanning vehicle developed by BridgeCat. This is owned by Department of Transport. So we managed to get this vehicle to the bridge, and so this bridge has a sonar scanning head at the end, and we placed that sonar scanning head underwater and took a riverbed profile. So this is the riverbed profile. Uh, so this is one bay of the bridge, and you can see this is that bay. So these are three sonar scanning images, 1, 2, and 3, and overlaid with each other. So you can see this is the North Bridge Pier. So this is that bridge pier, and this is the South Bridge Pier. This is South Bridge Pier. So, and we can see that this is the ground level before the repair started. And we took another sonar scan after the repair finished. And with that, we could show that. So this is the ground level before the repair started, and this is the ground level after the repair finished. So you can see, especially near the South Bridge Pier, there is a significant amount of ground backfilling. So we have so what we have is we have before and after scour, we have the riverbed level change. And right after taking the riverbed profile before the repair, we created a finite element model of the bridge, and this is that finite element model. So this is a standard finite element model. What's unique is actually we have used Winkler spring model to provide the soil pile interaction. So what we did was we produced this FE model, and we simulated scour by deleting the springs wherever there was scour. So for example, that South Bridge Pier, there was a scour over here. So we deleted the springs to represent scour, because scour is basically removal of the soil. So that means soil structure interaction is removed. So we found that estimated natural frequency according to the numerical model after backfilling should be around 17.1 hertz, and before backfilling scour it should be around 16.3 hertz. So this was before any instrumentation. So we found out that actually the expected variation in natural frequency was not very significant, 17.1 to 16.3. So we needed a very high sensitivity accelerometers. We took these Epson accelerometers, which have very high sensitivity and very low noise in the range of micrometers per second squared. And we placed 10 of those accelerometers at different locations of the bridge. And we placed 7 of those accelerometers along the edge of the bridge, along one vertical plane, so we can get the mode shapes along that vertical plane. Unfortunately, 2 of the accelerometers did not work. So we had 8 accelerometers providing uh, vibration, ambient vibration throughout the 6 months period during which the scour backfilling occurred. So this is me actually trying to have the balance. It's a very unique experience because uh, because placing accelerometers on a board, that was a very fun experience, and having the balance on a board is a real experience. So uh, so according to so this is the final result I got. So according to, so when I look at the natural frequency data, I found that the natural frequency data had a significant amount captured experimentally had a significant amount of variation. So, for example, the natural frequency that we captured for the mode 2 had its natural frequency at around 18.5 hertz, but that 18.5 hertz is like, if you take one measurement, it's 18.6 hertz, the second measurement is 19.1 hertz, third measurement is 17.5 hertz. So there's a significant amount of variation. So that variation accounted for from the mean value, it was around like 5%. So according to the numerical model, the estimated variation for 1.8 meters of scour was also in the same range. So unfortunately, although we captured the natural frequencies at this bridge, the, the natural variations we captured, the the experimental variations we captured were significant. So because of that, unfortunately, we could not capture uh, the level, the natural frequency change because of this backfilling process. And then what we did was we looked at, so if there was extensive amount of scour at this bridge, what would have happened? So for example, uh, we consider this blue line case. That is, if there was full scour along the South Bridge Pier, if the South Bridge Pier had full local scour, uh, because the scour at this bridge was only limited to part of the bridge pier. So if we assume the scour was along the full width, then we found, so after about 1.8 meters of scour, we would have seen the experimental uncertainty being passed. So that means the highest amount of scour depth resolution we can capture at this bridge is about 1.8 meters. So then if you consider, this is all conducted using numerical modeling. So if both the bridge piers had scour, so when we delete the springs along both bridge piers, we found that like after passing about 0.6 meters, we would have seen the natural frequency passing that experimental uncertainty. So according to this, we found that, okay, so the expected variation, the expected scour depth resolutions we can capture using this method is around 0.5 meters to about 1.2 meters range. So this was a bit of a discouraging finding, because we actually went to the bridge to capture natural frequencies, and we could not capture that. But we actually saw some other parameters that uh, indicated some indication of scour. So this has actually too much detail, but if so, this is the mode shape before and after the repair. And so this is showing the mode shape from one side. And so you can see this is the ground level, and this is the north span, middle span, south span, and this is the north pier and south pier. If you can remember, the highest amount of scour actually happened was there in the near the south bridge pier, and highest amount of backfilling occurred at the south bridge pier. So at that south bridge pier, according to the FE model and according to the experiment, there is an reduction. There is a reduction of modal amplitude because of the backfilling. Or on the other hand, because of scour, there should be an increase of the modal amplitude. So this is suggest, and also what's unique is that this modal amplitude increase is limited only to that bridge pier. So that means we can potentially use this to locate where the scour is located. So this was only like one of findings. So we wanted to study this. I'll show you some of the experiments we conducted in the laboratory to study this in detail. The second indicator we found was mean spectral density. This was also an unexpected finding. So actually this showed much clearer change. So when we look at the mean spectral density, oh, uh, actually this unit has to change. So when we look at the mean spectral density, uh, when we started backfilling scour in August to when we ended backfilling scour to November, there was a clear gradual reduction in the main model spectral density. So this is basically whenever we look at the model peaks of a mode shape, we have a model peak, and at that model peak, what is the power spectral density value at that model peak? So if we have plotted, so this is 120 points. Uh, these are different 120 points, and what is that peak value? And so as you can see, the peak value actually gradually reduced. And this is showing that there's some correlation between scour backfilling and so level of scour and the model spectral density. But these all these like although we found this in the field study, these could be some uh, one-off findings. So we wanted to study this in a laboratory environment where we can control the level of scour, control the types of bridges, and study and also control the types of scour to understand uh, how we can we actually capture the same variations. So there are some existing literature on laboratory experiments on this like vibration-based scour monitoring, but they have not been conducted on the geotechnical centrifuge. So, for example, some of the researchers have tried to uh, uh, have a, a bridge pier, like a small scale bridge pier, uh, on a like a soil medium and remove soil over here. But if you do that, there is going to be two problems. One is that uh, this bridge pier does not represent the behavior of a full bridge. And on the other hand, the soil structure interaction is inaccurate because soil structure interaction here does not represent a full scale soil structure interaction. To explain that, so if you look at a full scale soil sample, we know that with the with the depth, with soil, we have the effective stress is actually increasing with depth linearly. So there is a direct correlation with effective stress and the elastic modulus of soil. So the elastic modulus of soil increases as the effective stress increases. So if you look at a small scale soil sample, uh, although the soil sample is small scale, we should have actually the similar variation because it's the same soil, if the density is the same, and if the same type of soil, we should have the same variation. So the issue is that you can see that here the because it's the same variation of the elastic modulus at the corresponding depths of full scale and the and small scale, we have different amounts of elastic modulus. So the elastic modulus here does not represent the elastic modulus here. So this is with soil, as you can see, there's a dimensional component to uh, the the elastic modulus. This is unlike concrete or steel where we have the same elastic modulus everywhere. Because there's a dimensional component, if we scale down, we have an inaccurate elastic modulus profile. So this is a common problem, and for geotechnical engineers, what they do typically is test this in a geotechnical centrifuge. So we decided to do that, and to do that, we considered different types of bridges and different forms of scour. So we consider three types of bridges. So we considered a integral bridge. So integral is the connection from bridge pier to the deck is fully integral. That's the moment is fully transferred from the bridge deck to the bridge pier. And we scale this down by 60 times. And then so we test this in a geotechnical centrifuge package, which is about 850 millimeter. So there was not enough package space to test all these different models uh, fully. So we only considered for that this bridge, we considered the full bridge, whereas for all the other uh, types of bridges, we only considered the foundation. So bridge 2 is a simply supported bridge with a pile bent foundation. We only considered the pile bent foundation scaled down by 60 times. And also because a single pile provides a very simplified form to study, we actually considered a single pile as well. And also we wanted to study uh, what happens for a shallow foundation. So we considered shallow foundation model as well. And we conducted these experiments at Schofield Center at University of Cambridge. And so this center has all these facilities to uh, prepare a uniform soil sample, and we had sensors placed in soil, and also we placed all these different models as the soil layers were progressed. And so this is the geotechnical centrifuge, as you can see here. So this is so centrifuge is basically uh, a beam of about 10 meters in diameter. So this beam has two ends, and we can place in one of these ends we can place the centrifuge package that we prepared. So this centrifuge package has the this soil structure model, and what happens is we rotate this centrifuge beam uh, such that we get the effective centripetal acceleration equivalent to the required uh, acceleration we need. That's the 60 times g for most of the models here. And so these are centrifuge package. So these are different models I considered. So model 1, model 2, and model 3 and model 4. So if you look at one of these models zoomed out, so you can see that zoomed in. So you can see that this is model 1. So for model 1, you can see that this is the scar profile we created around the bridge foundation at the bridge middle bridge pier, and we had a actuator which excited the bridge model. And so this actuator, what it provided was, so as you can see here, so there was a load cell here, and this actuator can provide a impulsive excitation, and then we uh, measure this load input excitation using this load cell, and then we have a set of accelerometers placed on this bridge model to measure the response acceleration. And also we had another actuator for other models. So that is this actuator. So what we had was we had two air sources coming in here, and this is a air hammer basically, which is connected to a kicker, and this kicker has a load cell at the end, and then this load cell goes and hits the model. So and we have accelerometers placed on the bridge model to measure the response vibration. And so after conducting all these tests during when the centrifuge was rotating, we could find out the natural frequencies of this model of the various models. So if you look at one of these models in detail, so in y-axis, I'm showing the natural frequencies in the full scale. So basically, so in this the centrifuge model, we capture the natural frequencies. They are in the order of around 120 hertz, 130 hertz, and we can using centrifuge scaling laws, we can uh, take them to the full scale values, equivalent full scale values, by dividing these values by the equivalent scaling factor, that's 60. So by applying the scaling factor, this is showing the natural frequency in full scale, equivalent full scale, and these are showing the scour depths in equivalent full scale. So you can see that the natural frequency has reduced drastically from about 1.8 hertz to around 1.1 hertz. So this is a large change for about 3.6 meters of scour depth. And we have considered different shapes of scour. For example, we considered scour only at the bridge pier, and we considered 1.2 meters of scour, uh, and 2.4 meters of scour, 3.6 meters of scour. And then we, in addition to that, we added scour only additionally at the left abutment, and also scour also at the right abutment, and finally a global scour case where scour was uniform everywhere. So for each and every advancement of scour, we saw actually some increase of some reduction of natural frequency. So this actually shows that actually natural frequency is a very sensitive indicator for scour. And if you look at, so I had four models. If you look at the final result for all the four models, so if you look at the scour depth, if you consider the scour depth to be about 30% of the embedment depth, and for integral bridge, we saw that for local scour at one pier and both abutments. So that means if the local scour is placed everywhere, the natural frequency variation was about 37%. And if local scour was only at one bridge pier, the natural frequency variation was about 16%. And if the local scour was only at one bridge abutment, that's like the two abutments at the end, the natural frequency variation was about 14%. And uh, if the scour was throughout everywhere, global scour, the natural frequency variation was about 40%. So for pile bent as well, pile bent foundation, that's model 2 as well, we saw a significant variation of natural frequency. For pad foundation, unfortunately, we didn't see a significant variation that was less than 5%. For monopile as well, we saw a very significant variation. So although we see a significant variation here, if you look at, if you remember the field study we carried out, according to that, when we try to actually measure these in the field because of environmental variations, temperature variations, and inaccuracies, we have to remove about 10% of the natural frequency for errors of measurement. So if you actually, even if we remove that 10%, you can see that still there is a significant potential for natural frequencies to be an indicator of scour. So, and also the other interesting uh, thing here is that uh, for crack-based natural frequency studies, mostly the natural frequency variations they observed were less than 10% in most cases. But for scour, we actually see this experimentally. We were able to show that the natural frequency variations can be as high as 40%. And the second indicator, spectral density versus scour depth. So for one model, if you look at the spectral density versus scour depth, so this blue line showing the uh, no scour case, and then this one is showing there was scour uh, about 1.8 meters of scour equal 1.8 meters of scour, and this is showing 3.6 meters of scour, and this is showing uh, global scour. So these are basically increased scour cases as we go down. So you can see that similar to the cases of scour, so as we progress with scour, we actually see that the natural frequency has actually reduced. That's actually what we discussed previously. At the same time, the spectral density value actually has gone up as well. So from here to here, we have seen the natural spectral density value has gone up. And another finding actually, Dr. Hugh Hunt actually indicated this to me during my Viva. That's that uh, there is sort of a asymmetric behavior. If you look at these peaks, there's an asymmetric behavior. So the peaks are leaned more towards the right, the higher frequencies. That means that there is a stiffening spring effect here. That means a stiffening spring effect, as I know, is basically the effective stiffness provided by the system is increasing with time. So that means, so perhaps that may have happened in the soil structure interaction where, we have, when we have vibration, maybe there might have been ratcheting where the soil might have become stiffer as there is more vibration. So that may be what's suggesting here, because there's some leaning towards the higher frequency. Um, so if you look at the spectral density variation for all the four models, uh, we actually see significant variations. These are like huge variations. So the for the same case, if you look at the singular value of spectral density variation for about 30% of the embedment depth, uh, the variations are can be as high as 28 times the initial value. And but still, if you look at the field study, in the field study, I actually found that the variation can also be, the measurement variation can also be very high. So we have to remove about 50% for that variation. So if you remove, even if you remove that variation expected in a field, we can see that for all the models, we can actually see the model spectral density shows significant variation. So actually, in this case, we can see that model spectral density can actually be a significant, very valuable indicator for scour. And the other indicator was mode shape. So if you look at model 4, for model 4, the mode shape variation. So in this one, I'm showing with the lighter colors, I'm showing the higher scour cases. So for no scour case, 1.8 meters of scour, 3.6 meters of local scour, and 3.6 meters of global scour. As you can see, when we increase the level of scour, so that means the color of the line becomes lighter, you can see that the mode shape is actually increasing. The mode shape is actually normalized by the uh, mode shape amplitude at the top. So you can see that the mode shape is showing some increase of the modal amplitude here. So this is suggesting something we saw similar to the field experiment. That's the mode shape is actually showing an increase at the location where there is skull. And similar, but for model 3, that's the shallow foundation, we did not see a clear increase of mode shape. For the case of model 1, we showed, so these are different skull cases. So this dark line is showing no skull case, and then uh, these lighter colors indicating slightly higher cases of local skull at the middle bridge pier. And you can see as at this location, the with the lighter colors, you can see that the modal amplitude has actually increased here. But the issue is that here you can see that the modal amplitude should not actually increase here, but there it has gone up and down. So that is suggesting maybe there has been some errors of measurement, or mode shape is not a very very reliable indicator of scar, because there can be some inaccuracies. So that's all the experimental results. And then moving on to the numerical modeling that I carried out as part of my research. So existing research, so there has been a significant amount of research conducted by uh, uh, Prendergast and uh, Professor Gavin. And what they have done is that they have considered this vehicle bridge soil interaction system, and they have simulated the traversing of vehicles using this spring-based system. And how they have simulated scour was by simply deleting the springs. So if there is scour here, they deleted the springs because that means the soil has actually removed. So if you look at this in detail, so this is the no scour case. Let's say this is a bridge pier. And with local scour, what happens essentially is that there is a localized uh, creation of a scour hole, and but still the soil surrounding scour hole remains the same. So in this case, we have a kind of a doubt here, because the soil, in this case, we know that the soil stiffness increases with depth like this. But what happens after there is a local scour case? Because if we look at it from here, we can see that the spring, all the springs supporting all the soil structure interaction here is removed. So we can actually delete the delete or remove the soil stiffness here. But there is soil surrounding the scour hole. So because of that, there is some stiffness still remaining. And on the other hand, if you look at from here, you can see that all the soil is removed. So we can assume that the stiffness has to be zero here. So we have a doubt here whether the stiffness should be zero here, or the stiffness should be the same value as previous value, because there is soil surrounding the scour hole. And for the case of global scour, actually this method of proposing deleting the springs uh, cannot actually be used, because for the case of global scour, we actually have no soil at all here. So that means the soil stiffness profile, we can't just delete the springs. If you just delete the springs and have this same soil stiffness profile on wherever there is soil, that means we actually assume that there's some residual stress here. Uh, there's residual stiffness here. So because of that, uh, that's not going to happen, because there's all the soil is removed. So because of that, we can see that there should be actually ideally a reduction of the full stiffness profile down. So in this case, we actually should have a shifting down of the stiffness profile. So in my research, I proposed, so this method of existing method of deleting the springs wherever they have a scour is more suitable for local scour, and shifting the springs down is actually more suitable for global scour. And I'll just explain one of these models I created. So for bridge one, that's the full bridge, I created this numerical model. So, and for the full bridge. And This is a standard numerical model. This is created using CSI Bridge software, and we used link elements to show either the fixity or uh, Winkler spring model. And what we found is that for these two cases, so previously I showed you the experimental result, and according to the numerical variation, numerical estimates, we actually got a very close estimate of the natural frequency variation. There's about 5%, 10% error, but reasonably speaking, the numerical case of local scour simulation and numerical case of global scour simulation matched with what we observed in the experiment, because this is the global scour case, and up to here there is all local scour cases. So, and when I simulated the local and global scour cases for this bridge using numerical modeling, I saw what I saw in the field study, that is that whenever there is scour, so for example, if you look at here, so these are different, uh, so this is showing different cases of scour only at this bridge foundation. So if there is 1.2 meters of scour, 2.4 meters of scour, and 3.6 meters of scour. So if there is local scour only at that bridge foundation, according to the FE model, the increase of modal amplitude is localized to that bridge foundation. So this is suggesting actually there is we have the potential to capture uh, the variation of scour at bridge foundations as a localized increase of modal amplitude. But experimentally, we saw that variation, but it's not very clear experimentally. So comparative limitations and advantages of this monitoring technique are that one of the limitations is that the maximum possible scour depth resolution is about zero point 0.5 meters to about 1 meter, but not centimeter scale resolutions as in sonar. For example, if you can remember the sonar scan profile I showed you, uh, that we captured during the field experiment, that's actually provided centimeter scale resolutions, but with vibration based methods we can only go for about 0.5 to 1 meter resolutions. So, and also we can only measure a change, but not the scour depth directly after the first measurement. So, for example, with sonar, we can go to a bridge, we can do the sonar scan, and we can say, okay, so this is the level of scour. But with vibration-based techniques, we can't go to a bridge, place accelerometers, and say, okay, this is the level of scour. We need, we can only capture a change, so we have to measure vibration for a long period of time. So the comparative advantages of these techniques are that there's no underwater equipment, unlike most of the other monitoring techniques. This is actually I think probably the only monitoring technique where we do not need any underwater sensing equipment, because we actually measure the vibration of the bridge. And also this has the capability to become a remote, continuous, and real-time monitoring technique. So in summary, we were able to demonstrate the potential of a vibration-based monitoring techniques using a field trial, centrifuge modeling experiment, and associated numerical modeling. And so this is actually, I copied this from my thesis, the first conclusion of my thesis. A vibration-based monitoring technique examining the combined effect of three vibration-based parameters, that's modal spectral density, shape, and natural frequency, has the potential to identify and locate changes in scour depth at bridge foundations to approximately about 0.5 to about 0.6 meters for local and global scour. And for one third of embedment depth, for 30% of the embedment depth approximately, we studied in this experiment, we saw that the natural frequency changes by about 3 to 40% according to the centrifuge experiment. And mode shape showed an increase only near the foundation undergoing scour. So that means we can actually potentially use this to localize where the scour is located. And modal spectral density showed a huge change of about 140 to 2,800%, and the error of measurement is in the range of 50%. And also, all these three parameters showed more sensitivity for global scour than for local scour. And also, we found that bridges with deep foundations and integral decks have most suitability for this monitoring technique. And research outreach, actually, this research got a wide coverage recently, and some of the findings of our research, for example, finding about 40% variation of natural frequency during the using the uh, centrifuge model. That actually went to New Civil Engineer, ASC, and the Engineer magazine, and also our field study got nominated for the British Construction Industry Awards and Highways UK competition as well. So with that, actually, so this has been actually a very fun experience studying about vibration. And so I want to really thank my project team, Professor Campbell Middleton, Dr. James Talbot, Paul Fiedler, Professor Gopal Madhabushi, Dr. Stuart Hay, and all these fabulous people who supported me during this research to carry out this research. Thank you very much. Yeah. And I'm really looking forward to hear your thoughts on this research because you are really the world's experts in vibration-based monitoring.
All right, thank you very much, Kasun. If anyone has any questions about the presentation, they can use the raise your hand option. Tora has a question.
Yeah, thanks very much for the interesting talk. I was just interested if you had thought about or tried to take account of the water depth and whether that contributed at all to some of your experimental uncertainty.
Mm-hmm. Yeah, so in my experiment, for example, the centrifuge experiment, one of the assumptions I made was that the level of water and the saturation does not have a significant effect on the variation of natural frequency. So there are some researchers, for example, Prendergast and Professor Gavin, they have actually studied this using different bridge piers in a small scale. And what they have found is that given the bridge pier is stiff, the natural frequency does not get affected much by the level of water. So assuming the bridge pier is stiff, we can actually assume that the effect of water depth is not very significant. But
okay, that's interesting.
Okay.
Yeah. Thank you.
Thank you.
Do you have any? No. James has a question. Hi, James, can you hear us?
No,
sorry, thanks.
Yeah.
I just wondered whether you wanted to say a little bit, Kasun, about how the bridge was excited.
Yeah. Do you mean? Oh, you mean the bridge, Belden Bridge?
Yeah, yeah. Oh, yeah. Sorry, I did mean Belden Bridge.
Yeah. So Belden Bridge had the vehicle, so this basically ambient vibration.
Yeah.
So if you look at this one, so they have a large number of vehicles going over the bridge, and so what we did was we considered all the measurements we took, like because we had measurements throughout the day, but we only considered the measurements during peak hour traffic. That's when there was a large number of vehicles passing the bridge. So we assumed that because the vehicles with like different weights and different vibration-based properties pass the bridge, we assume that there is sort of a wideband input for the 10-minute data sets we considered.
Yeah, good, thanks.
Yeah. Thank you.
I see Hugh on his hand raised.
Well, thanks, Kasun, for that. Good to hear how things have been going. At the beginning, you said that 50% of bridges fail on account of scour. When you say fail, do you mean they don't actually fall down? Is it just that they are forced to close or to reduce traffic? Or do you mean that 50% of bridges actually collapse because of scour?
So
50% of bridge collapses are collapses due to scour.
This is actually collapses. Yes, these are collapses, because if you look at so this is a large. So from 1989 to 2000. So as far as I can remember, it was collapse, but I'll have to check it again because it could be there was large cracks and needed repair. But as far as I can remember, there were collapses.
And this is in the US. What's the situation in dare I say in countries which perhaps have worse problems with infrastructure maintenance, or perhaps the US is pretty bad. I shouldn't suggest that the US is good. The countries which have lots of flooding and lots of perhaps fairly where the bridges maybe not in such good condition as in other places.
Yeah, for example, Taiwan has lots of flooding problems, and I've seen lots of scour-based studies being carried out in Taiwan. And so in my actual thesis, I explained like references to like different countries. So for example, New Zealand, Taiwan, China, and UK. Actually, if you look at almost all the countries, the scour is actually clearly the largest cause for bridge failures.
So I remember as a kid, we used to go to riverbeds to go swimming, and we quite liked those. What you've got in that picture there, we quite liked those kind of mini little lakes because the water was nice and warm. So we didn't think of them as being a problem. We thought they were really good.
Thank you very much for that question. Do you have any?
I just want to say, I'm afraid I have to go now because I've got to get ready for another call at 5. But thank you very much, Kasun, for your talk.
Thank you. Yeah, thank you very much. I was wondering, like, whether like can you, like, when you look at this vibration-based model spectral density change, I was wondering, what is your opinion? Like, what do you think is the cause for that? Like, as experts in vibration, yeah, Tore.
Not a claim to be the expert, only it was linked to a question I had, which is I wondered whether you'd thought about possibly damping as an alternative metric, and whether that was maybe part of the explanation for the change in the height. It looked like in those plots you had quite a broad peak that then became a sharp peak, which is perhaps connected to damping. Exactly. And damping is often associated with the boundary conditions, and it's the boundary conditions that are changing. So I wondered what your thoughts were on that.
Yeah, so let me get that slide again, please. Yeah, so this one. So actually, yeah, so when we saw that, we actually thought damping was the main reason. And we looked at damping using the half power bandwidth of, not this one actually, of the frequency response function. So this is actually a singular value. So this is only looking at the output only values. We looked at the frequency response functions. And for that, we actually found, using the half power bandwidth, we calculated the damping values. They showed some variation, but it's not clear variation. Maybe that's because clear variation means in the sense whether the damping is reducing significantly because of scour. We showed some, it's reducing, going up, going down with, like, it's I don't know whether you understand, like it was not a damping values we estimated were not very clear cut, as like similar to the clear cut change we saw with the singular values.
Okay, that's interesting. And the singular values are kind of a combined metric across all of the different accelerometers, is that right?
Yeah. Yes, exactly. Yeah, singular value is basically giving like a power spectral density of all the accelerometers.
Yeah, so maybe that's a nice systematic way of averaging across all of them, or extracting the most information from all of them.
Exactly. So we calculate singular value by using frequency domain decomposition method. And using that, so basically we take the power spectral density matrices of all the sensors, and then like, so we get the power spectral density of matrix of all the sensors, and then decompose that to get this singular value.
Interesting. Okay, thank you.
Yeah, so perhaps actually what I feel is that I also feel damping may be the main cause, but maybe because damping is actually very difficult to measure, right? So there's huge inaccuracies, right? Maybe that's also James. Yeah.
Well, you kind of taken the words out of my mouth, then, Catherine. I was going to just um, remind people that Belden Bridge was a real challenge, wasn't it? Because actually,
Yeah.
it's quite a substantial bridge. I mean, it's masonry and concrete, and it's a sort of a fairly short span squat bridge. So we were all pretty pleased to get any measurements at all.
Yeah,
If
exactly.
I remember rightly.
Yeah, that's a good point. Yeah.
So yeah, estimates of damping was quite probably a long shot, if we're honest. Yeah.
No, it was interesting to see how striking it was for the bandwidth change for the singular
That
values.
really
Exactly.
that behavior is it's intriguing, isn't it?
Yeah. So actually, when we got this data, like for the Belden Bridge, we actually thought, okay, so although we got that for Belden Bridge, we might not get this for the centrifuge test. But for all the four models, we actually got this clear gradual increase with the model spectral density increase with the scour depth. So what's interesting is actually, I mean, we know like model spectral density has some correlation to the input excitation, right? So if you give higher input excitation, the model spectral density will also go up. Although that is there, and like probably there will be higher excitations, low excitations during this whole 6 months of monitoring period, and also during this centrifuge study. But however, the spectral density is just going up. So maybe there's very significant correlation to the scour depth.
Yeah. Jim might have something to add there.
I was just these comments saying damping is hard to measure, all perfectly true. Actually, in the centrifuge test, it might have been much easier to monitor damping, and you were using a little striker, so you had transient results, and you might have been able to get the log deck rather directly out of your transient excitation in the centrifuge. Did you try that?
I used only I used the whole one. You're meaning only using the transient, so the initial value rather than the free vibration part.
No, using the free vibration, but measuring the decay rate. That's sometimes a better way to measure damping.
Ah, okay, that's a good idea. I'll try that.
Frequency domain method.
I didn't try that. I only used this because this actually like this we got this finding really near the my writing of my PhD thesis, so we didn't have time to study about damping much as well. But this is something good. I'll study that, looking at the decay of the damping, decay of the transient.
Yes, I mean it should be one of the powers of a centrifuge test is that you've got much better control over nearly everything. Still difficult to do measurements on your half a ton of whirling stuff in a bucket, but nevertheless easier than the real bridge, I should think.
Exactly. Yeah. I'll try that. Thank you very much for that suggestion.
Are there any further questions from the audience? Right. I think thank you very much, Kasun, then for your very engaging talk today. And I hope you got something out of meeting the dynamics vibration group.
Yeah, it is fun. Yeah. Thank you very much. Yeah, thank you.
So I'll just for the final items of the talk, I'll just briefly mention that next week we have a talk from one of our newer from one of our second year PhD students. So Samir Abdel Mauti will be giving a talk about his PhD work, which is on passenger discomfort during longitudinal vehicle motion. So I hope most of you will be able to join us next week to hear about his interesting talk then. Yeah, so thank you everyone for joining in this week's Tea Time Talk. And I hope you'll have a great weekend.
Good.
Thanks very much for the talk.
Yeah, thanks very much. Yeah, bye.
Thank you very much. Yeah, thank you.